Okay, friends, let's see what this one has. As I keep saying, feel free to pause this video whenever you wish. If you want to think ahead, use your own brain and not just copy my thinking. It would be helpful for you as a student, and it would be a good decision. And let's see what this question has. We're given some polar curves, r equals 4 and r equals 3 plus 2 cosine theta. They intersect at pi over 3 and 5 pi over 3. So I can see we have this shaded region R, right in here. So it looks like R, I'm just processing. If we had this region, and I took the pink region, or the area for the circle, this whole blue circle, well, that sector of the circle, and I subtract that purple part I shaded, it looks like I would be able to find the area of R. Now, since this is a polar question, well, it starts with a polar question, we could go all sorts of different ways. They could start talking about some vectors and, points moving along the curves. They could talk about, obviously, the area. And there's like jumping between rectangular and coordinate systems. There's a number of different places they could go. Since this is a non-calculated question, they gave us the intersection points so we didn't have to figure that out. If you had to figure it out, I'm going to show you how. So if you had to figure out where these things intersect, just set them equal to each other. And subtract that 3, you'll have 1 equals 2 cosine theta. And then divide by 2, so you have 1/2 is cosine theta. And then you figure out where the cosine theta is 1/2. You should be able to process that that's in the first and fourth quadrants because that's where cosine is positive. Hence the pi over 3 and 5 pi over 3. All right, let's see what they have for us. Part A. R is the shaded region inside 4 and outside 3 plus 2. Write an expression involving the integral to find the area of R. So what I said was if I integrate the r equals 4, which I think I made light blue, if I integrate the r equals 4, you could just use geometry also, but I want to do things similarly. So if I integrate from pi over 3 to 5 pi over 3, 1/2 r squared d theta, that will get me the circle. And I take that circular region, and then I need to take away this part. So I need to subtract, I guess I could have done this as one integral, pi over 3 to 5 pi over 3 of r squared, 3 plus 2 cosine theta squared d theta. And that should get me what I want. Now be careful, because area you have to think of differently. It's 1/2 r squared d theta. If you're confused why, let's see. One way we can think about it is think of a circle. And if I want to find the area of a sector of this circle, let's say that this is theta. Well, the area of the whole circle is pi r squared. The sector of a circle, so the fraction we're looking at is theta over 2 pi, because 2 pi is the total number of radians in the circle. Theta is the number of radians I'm looking at. And if you can either set that up as a proportion. Yeah, let's do that. So the top of this fraction is the part, the theta, to the whole, which is 2 pi. And then the area of the circle is pi r squared. And then the area of the sector, which is what I want to find, is on the top. So part to whole, part to whole. And then multiply by pi r squared. And I'll have that the area of the sector is pi r squared theta over 2 pi. Cancel out the pi's and you get r squared theta over 2. Now, because this is calculus, we make those thetas super duper small, infinitely small. So it's r squared d theta over 2, and we add them all up with the integral. Hence the r squared d theta over 2. I put the 1/2 in front. If you want to divide the whole thing by 2, that's totally fine too. Let's see what part B. Ooh, the slope of the line tangent to the graph. Well, slope is a dy dx question. So I want a dy dx when theta equals pi over 2. So let's go ahead and think. I want a y equation, because I can think of this as dy d theta over dx d theta at theta equals pi over 2. And let's see. In polar, if I draw myself a picture, I have some point here, which is r theta. This is theta. This is r. This is x. This is y. So the sine of theta is y over r, which means y is r sine theta. So then, a couple ways we can take this derivative, but dy d theta, I'm going to do product rule, is dr d theta sine theta plus r cosine theta. And I want to know dy d theta at pi over 2. So dy d theta at pi over 2 is going to be dr d theta. So dr d theta is negative 2 sine theta. And sine of pi over 2 is 1, so that's negative 2. Sine of pi over 2 is 1. R, so if I plug in pi over 2, cosine is 0, so that's 3. And then cosine of pi over 2 is 0. So dy d theta is negative 2. So I wrote an equation for y. I took the derivative in terms of theta using product rule. And then I plugged things in. And I found dr d theta from going back up above. So dr d theta was negative 2. I bet I'll need that again. Similarly, the cosine of theta is x over r. So x is r cosine theta. I like to build it that way in case I forget. So then dx d theta is dr d theta cosine theta minus, I'll show you minus y. The derivative of cosine is the negative sign. So then I need to know dx d theta at pi over 2. I already determined that dr d theta was negative 2. Cosine of theta is 0. R is 3. And then the sine of theta is 1. So that's going to be negative 3. So then, my last step, dy d theta over dx d theta is going to be negative 2 over negative 3, which I could write as 2/3 if I want to. And is that all I need to do? Slope of the line tangent. Yes, so I found the slope. Is that all? That took me several minutes to do. So let's recap that quickly. I wanted to find dy dx. I've thought of that as dy d theta over dx d theta. You can think of it as the fractions canceling each other out. I then had to think, okay, in polar, how do I write x and y? So what I did is I drew that orange triangle to help me visualize what was going on, where I had a theta and an r and an x and a y, and found the relationship. I took the derivative, don't forget chain rule. Because I'm taking the derivative with respect to theta, I have dr d theta popping up, and then I plug things in. What does part C have for me? Particle moves along a portion of the curve, 0 to pi over 2. Particle moves in such a way that distance between the particle and the origin increases at a constant rate of 3. The distance between the particle and the origin increases at a constant rate of 3. Okay? And that is, so the distance between the particle and the origin. So the distance between the particle and the origin. So we're traveling along this thing. Oh, that's just the rate of change of that. So that sounds scary, but that's dr dt. The rate of change of the radius is 3. Find the rate at which the angle changes. So I want d theta dt. at the instant when the position of the particle corresponds to pi over 3. So I need the position of the particle to be pi over 3. Okay. And I know what r is. So r is 3 plus 2 cosine theta. So let's go ahead and take a derivative. Because dr dt is going to be negative 2 cosine theta d theta dt. And then when theta equals pi over 3, dr dt is 3, because that's a fixed thing. Then I have the negative 2 cosine of pi over 3, and then d theta dt. And I get that's 3. Oh, I never took the derivative cosine. Silly me. I was looking at this like, wait, the original function had the same thing. So that should be positive. Fix that. Positive sine, sorry. And then 2, sine of pi over 3 is root 3 over 2. And then d theta dt. That was a close one. So I need to fix that up above too. And make that a sine. I was so excited I forgot the most important piece here, or one of the most important pieces, right there. Oh, that should be a negative. I'm sorry. That should be a negative. I was correct originally to have that negative there. That's interesting. I did the negative, but I forgot to change it to a sine. And negative. Okay, so my 2's cancel out. So d theta dt is negative 3 over root 3. Now, I kind of butchered that, but that's okay. And so my answer is, you could rationalize that if you want, negative 3 over root 3, but you don't have to. Indicate units of measure. I have no idea. Let's see. dr dt was in units per second. d theta dt is in radians per second. So this per seconds go away. And then it's units. Actually, I'm thinking too hard. So d theta dt is the radians and then seconds. So just radians. I got myself twisted up there. Per second. And so let's recap because I was a little wonky. So r is 3 plus 2 cosine theta. So I knew what dr dt was. I wanted to know what d theta dt was. So what I did is I just took the derivative. dr dt is this negative 2 sine theta, which I messed up originally, but now we have fixed. d theta dt. I then plugged in pi over 3 for theta. Got 3 is negative 2 sine theta d theta dt. And then negative 3 over root 3, which you could rationalize, multiply by root 3 over root 3. You just get root 3. Okay, so let's look at this whole question. So the whole question, there's a whole bunch going on here. We have area between two polar curves. So that's that 1/2 r squared d theta thing that we discussed earlier. And you had to subtract the two pieces. Make sure you think about area in terms of connecting like this, not area like we did under coordinate grid. Find the slope. So slope is dy dx. We thought of that as dy d theta and dx d theta, and put those pieces together to find the slope. And then particle moves along, so that's a rate question. And you knew what dr dt was. You needed to find d theta dt. A lot going on in this one particular question. And let's see how we did. First one, I wrote it as two different integrals, but those are the same. Second one, let's see, what did we do? They told me my values. Okay, so we did this top way. And let's see what they did in the bottom. Oh, they distributed, okay. So in the bottom, they got rid of the r and plugged it in. To me, that looks a little messier. So I don't know that I would do it that way. But whatever makes you happy. And then for C, okay, so they broke dr dt into dr d theta dt and found those two pieces. It's the same idea as what I did. And then they solved for d theta dt. Yeah, Okay, so it's the same idea as what I did, and we got the same answer. So we did a good job.